Okay, so how is everyone today? Good. All right. So we've got a few more things to say about transformations of functions. To cover the very end of last time, what we said was that we could say let y equal f of x be given. In the first place, we could say, well, if this is what if this is what the plot looks like, so something like that, if that's the plot of y is f of x, then we can make a horizontal transformation, a horizontal shift of C, which is just to say that, you might say, well, I want to move it 5 feet to the right or whatever. So then C would be 5. So a horizontal shift of C, the new picture would look something like this. So the only thing that it's doing is it's moving, let's say, to the right. It's not moving up and down at all. Maybe it ends up looking like this. And then we could measure, where was it initially? Initially it was, like right there. So that point moved over that much, and that's C. Then what's the equation for the new thing? So because it only moved horizontally, that means that we didn't play with y, because y represents the vertical coordinate. So it's still going to be y equal. And because it's the same shape, it's still going to be f. Because the motion was horizontal, that means that x is going to be changed. So what's going to be the new x? X minus c. And again, I want to mention that the thing is moving to the right. Okay, the object. And then often students sort of look at that and say, but it looks like you're subtracting, so why is it not moving to the left? Well, the actual truth of the matter is that something is moving to the left. What's moving to the left? It's not the graph, not the red. It's not the red that's moving to the left. It's the axes, right? Because you could say I'm going to take this red thing and then pick it up and move it over there. You could say it that way. You could also say, well, I'm going to pin that red thing down, so I'll just hold it down there and then grab the axes and pull the axes to the left. If I did that, then that's what you would see. That's why it's a subtraction. Similarly, if from here, instead of doing a horizontal shift, if we do a vertical shift, of, say, k, that would mean that, okay, now we're going to take that thing, we're going to take that, and now I'm going to move it not left to right, but rather just up and down. So I'll move it up a little bit, say to like right here. And then you could mark, where was it originally? Originally it was about right here. And so you can say, okay, that's how it moved. It moved up. And then you get out your ruler and you measure that to be C. Okay, then, so since this is a vertical motion, that means that what variable did we play with? Must have been playing with the y's. And because there's no horizontal motion, that means that the x's must be unchanged. So the right-hand side is still going to be f of x. And what's the left-hand side? y minus c. Y minus c. So again, with the, you might say subtraction, I expected it to be an add, because after all, the thing went up, right? So I thought it would be an add. Well, the thing is that in the motion from that one to that one, something really did move downward. What moved downward? The axes moved downward, right? It would be just like saying, you could say, oh, I like this whiteboard here, but maybe you could move it up a foot. Okay, well then one way I can do it is I can just sort of pin the whiteboard there, right there, and then I can hire a crew to come in and rebuild the building 1 foot lower. right. That would work. That's what that's saying. Now notice that the rules of equations being what they are, that you can actually move the c to the other side, like this. But notice that in this case you can't get the c to move to the other side because it's inside of the argument to f, so it can't be moved. So this one can be seen in both ways, but that one only in that way. So to that extent, I could say, give an example like this. I could say, would you please plot the square root of x? And then once you've done that, I want you to plot. How about this one? Y is equal to the square root of x minus 2, like that, and then plus 4. And then after you've done that, so this one I give you the equation I asked for the plot, and on the last one I'm going to give you the plot and ask for the equation. Well, I got to wait for you to do this before I draw it, right? So what does this one look like? Right, and in some sense it begins where? At the origin. So square root of x, that's something that you're just expected to know. Okay, and as for the last one, I'll say that, I took the square root and I moved it to right there, and the coordinates of that point right there are -3, -1. And I want you to find the equation. All right, so in the interest of time, this represents two motions concerning starting with that one. So because the 2 is close to the x, I'm pretty sure that 2 must have something to do with a horizontal motion. Right? That's good. But what does that 4 have to do with? That's a vertical motion. But wait a second, it's not. If it's a vertical motion, it ought to be close to the y's, right? And it's not. So what do I need to do to make that clear to myself? Right. So if I move the 4 over, then it looks like this: y minus 4 is equal to square root of x minus 2. So doing that, to me it's more clear what's happening. It's saying that because we're doing subtract 2, that means that the axis is moving left 2. The background is moving left 2. Alternatively, how's the object moving? How's the red moving? Right 2. Okay, so this y minus 4, that's saying that the background is moving down 4. Background is moving down 4. An equivalent way is to say, how does the object move? The object moves up 4, right? So this bit is saying that the graph is going to go up 4, and that bit is saying that the graph is going to go right to GHT. Okay. So if I just if I single out that point at the origin right there, then I'll just move that point right 2 and up 4. So if that's 2, then that's 4-ish right there. Oops. So something like that. Any question about the middle one? Okay. So then what's the equation for the one on the right? Okay. So right. So then you know, this point right here from the origin, it went left 3. Went left 3. So then that would mean that the right hand side is square root of x plus 3. Why plus 3? Correct, because in that view, it's like saying that I pinned down this red bit here, and then grabbed the axis and move the axis to the right 3 units. I grab this, you know, grab it, and then pull it over, and so you'd that apparent motion you'd witness the red moving to the left. Okay, and then what's the left hand side? Y plus 1, because that's saying that the axis went up. And you know, if you had a mind desire to do it, you could instead write y minus -1, and you could also write x minus -3. There's nothing wrong with that. Yes.
Okay, so is the middle one the x minus 2? Does that mean that the graph moved to the left 2 then?
No, the graph went to the right. The axis, the graphite, the T bit, the T moved left.
Okay.
So it is to say, like this. If there's only two objects in the world, okay, just my phone and the pin there, and you can't see anything else, I can make the pin move to the right by doing this. Watch the pin move to the right. Bzzz, right? So what I'm saying is that you know, you imagine, you know, so you can imagine taking this and then moving it up, and then it looks like that, right?
Right, I was more getting my wording confused. I got that the axis is moving. I was getting my wording.
Okay, yeah. So I'm calling this bit, the red bit, the graph, and I'm calling this bit. I'm calling that the axes. Other questions? Yes?
For the middle one, the y equals square root of x minus 2 plus 4. So if we were given something like that on an exam, wax, would we have to format it the way
This
we
way?
want them to get 3 points? Or is that
No, not necessarily. But I mean, here's the deal. We're about to talk about a couple more transformations, and the thing is that if you don't sort of put it in this form, and you go on to make a mistake, then it's not clear what the source of your mistake was. You see what I mean? So, you know, if any reasonable person would say that showing every single step of work takes 10 steps, you know, then a reasonable grader might say, well, they showed 6 steps, but all of them were right and they achieved the correct result. Then, you know, a reasonable grader would probably say, yeah, that's all the points or most of the points. But if it takes 10 steps and you show 6 steps, and also you make an error, then it's not clear where the error is. And so, you know, generally, in such a case, graders err on the side of you had no idea what you were doing. Other questions? All right. So besides moving stuff around, just taking it and moving it to a new place, we can also make things bigger or smaller. We can make them bigger or smaller horizontally, so like stretching them, like this, stretching it out or compressing it, and we can do the same thing vertically. So these are called scales. So scaling. So in the first place, we can have a horizontal scale. Okay, so suppose that we have an f. So here's an f. Okay, and I've purposefully made those 2 points a different distance from the vertical axis. So one of them is kind of far away, and the other one's kind of close. Okay, so then. So what I would like for you to imagine is that I'm going to grab hold of that the red there, and they each have coordinates, and the horizontal coordinate of that one is negative, and the horizontal coordinate of that one is positive. And what I want to do is I'm going to double their coordinates. So that means that if that's -3, then the new one is going to be -6, and if that is +1. Then I'm going to double it, and it's going to become +2. So I'm going to take it and do that. But I'm not going to like pick it up and move it up and down or any of that. Okay. So this is going to be this is what a horizontal scale looks like. So this is going to be by C, and then in this picture. In the picture, I'm going to do C as 2, but just for something definite to look at. I say, all right. So to give myself a way to draw it, I'm going to draw where those 2 points are. In fact, these 3 points are. So I'm going to draw those 3 points right here. So they're here, and here, and here. That's where they were originally. Okay. So there's not a scale, so we can't, there's not tick marks, so I can't like read off the coordinates. But, suppose that the horizontal coordinate of that point is -3, then what will the new one be? -6. So it's going to be twice as far away. It's going to be over here. And where's that one going to go? A little bit to the right. Okay, like right there. So it now is twice as far away. And where does that one go? Stays there, right? What's its horizontal coordinate? 0, right? And what's twice 0? 0. So in fact, that point doesn't move. So the new thingy looks like this. So I took the red and stretched it out. Okay, and you can imagine I could have done the same. I could have squeezed it, and compressed it. So to understand sort of the idea, here's a fun prank that I wish I could do, and it wouldn't be super expensive and illegal and everything. But so like this building, right? You can imagine how funny I think it would be funny is if one night I just took all the doors, and those doors are 36 inches wide. That's the standard width of a door. And what if I just like made them all 18 inches wide? Wouldn't that be funny? What would everyone do? To have all the doors are like that. That would be I could achieve just as much humor, but probably far more illegal anyway. Is if I doubled the width of everyone. Just everybody's now twice as wide. The same effect, right? Make all the doors half as wide or make all the people twice as wide. So what I want you to see is that one way to think about this is I grabbed the stuff and I stretched it out. I grabbed the object and stretched it out. Another way to think about it is that I took the axis, I held the red thing fixed, and I squeezed the axis. Okay, so there's two equivalent points of view, right? So I could, concerning you and the prank, I could say, well, I'll just leave you alone, and then I'll magic the door until it's half as wide. Okay, or I could leave the door alone and then magic you until you're twice as wide. Okay, so if this is y is f of x, then what is this one? So because it's a horizontal transformation, which variable did we play with? Must have played with x. And which variable did we not play with? Y. So the left-hand side must still be y. And it's still going to be f because the overall structure is the same. But we must have played with the x coordinate. How did we play with it? It's not times 2. It's not multiply by 2. It's divide by 2. So, and in general, it's c. Now you might say, now wait a second. It looks to me like the object got bigger. Then why are we dividing? Because it wasn't that it wasn't. So we've got the world, okay, and we've got the object in it. It's not that the object got bigger. It's that the world got smaller, right? So this is saying, you know, in this picture, you want to make the red thing bigger. You want to stretch it out and make it bigger, make the red thing bigger. The way that you achieve it is actually you make the world smaller. Okay, interesting. So now that we did that nice and slow, we can do this one. Suppose we want to do a vertical scale. And suppose that this is the picture. So I marked those 3 points because I'm going to vertically scale it. Specifically, what I'm going to do is I'm going to vertically scale, for the purposes of the picture, I'm going to do 2, but you know, it could be anything. So just to make a definite looking picture. So this is a vertical scale by c. So in the picture, c is 2. What that means is that we're going to leave all of the horizontal coordinates alone. We're not going to play with them. But what we are going to do is we're going to take all the vertical coordinates and we're going to double them. We're going to double them, which means that if the vertical coordinate is positive, after doubling it, it's going to be even more positive. And if the vertical coordinate is negative, after doubling it, it's going to be even more negative. And if the vertical coordinate is 0, after doubling it, it's going to be 0, right? So, in fact, these 4 points, I'll mark those 4 where they were. So this one was there-ish, there. That one's fine, I don't need that one. And then that one, and that one. So those green points are those green points. So what I'm going to do is I'm not going to move those points left and right at all. Rather, I'm just going to double them vertically. So where do I need to draw a point so that this one will be, its vertical coordinate will be doubled? I need to go down, right? Because it's negative. About right there, right? So however far that is, I need to go that much further. So like right there. Okay, what's the vertical coordinate of that one? It's 0, right? So doubling it, it's 0. All right. What about that one? Its vertical coordinate is positive, right? So where do I need to draw the new point? way high, right? Like that high. So it's the same left and right, but it's twice as high, right? That high and then that much further, like right there. And what about this one? Higher, right? Okay, so the picture looks, according to my eye, something like this. Now, it's not an art class. But all the vertical coordinates have been doubled. Okay. So let's write down the transformation. Y is if this is y is f of x, then and this is a vertical scale by c, then because it's a vertical scale and we did nothing horizontally, which variable is unplayed with? X is unplayed with, right? So it's you know, nobody messed with x, and because it's vertical, that means we must have done something with y. So y becomes what? Y divided by c. C, right? Not 2. And you might look at that picture and say, you know, and you might say, like, wait a second, you made that thing taller. How could it be that you're dividing? Well, it would be the same sort of deal. Like, what if, as a different prank, I, you know, overnight I made all the rooms in here half as tall? You know, then you'd be able to like reach up and touch the ceiling, and that would be just like you being twice as tall. Right? So then, to make the object bigger, to make the red thing bigger, instead we're making the whole world smaller. Now, as it happens, in this format, we can again solve for y, and we can get that y is c multiplied by f of x. So those are both fine. The book writes it this way. But I think it's important to think of it, at least be able to think of it in this way, because as for this c that's inside of the argument, you can't get it out. It doesn't come out. All right? So an example, I can ask and say, all right, as for something you're supposed to remember, would you please remind me and plot, what does the absolute value function look like? And then once you've done that, so by the way, what does it look like? It's a V, right? So I'll draw that. Whoops. So it's a V. That's what it looks like. And one of the points on the absolute value function is how about this one? So that's, I'll say, the point 3, 3. Right? Because if you plug in x is 3 to the absolute value, what comes out? 3. So 3, 3 is one of the points on there. Suppose that I make a new picture, and it looks like this. So that'll be the point 3, 1. Do I want to do that? No. I want to make it, in fact, 3, 0. That'll make our lives slightly easier. So ignore that one. Unfortunately, I drew it in red. So that's 3, 0 right there. Okay, and then 3, 0. And now I want to put a point where? I want to put a point at, so this will be 6 and 6, like that. Okay. So just ignore that that thing right there. So all right. There's two motions that happened. Two motions happened. And there's sort of 2 points to look at. Because the absolute value is shaped like a V, the bottom of the V, the pointy bit, you can see that the pointy bit moved, right? How did the pointy bit move? To the right, 3 units. Okay, so as a result, because it moved to the right 3 units, that means that we know what happened to x. What does x become? Yeah, x becomes x minus 3. Okay. So because that point went right 3, what we're saying is that as a result, x has to become x minus 3. All right. So now notice that what is the distance between these 2 points right here? So between that one and that one. What's that distance there? That's 3, right? So the horizontal distance between the corner and that point that I singled out is 3. How about the horizontal distance between the corner and this other point I'm singling out? What's that distance? 3, right? So that means that in some sense it all moved over as a thing. But how tall is this point initially? 3, right? So it started out with height 3. And how tall is it now? It's 6, right? So so what happened to its height? It doubled, right? So its height doubled. So that's telling us how the y changed. So is that concerning the verticalness? Is it a vertical change? Is it a vertical shift, or is it a vertical scale? It's a vertical scale. So that's telling us that y becomes what? Y over 2. Because it was at height 3, and then now it's at height 6. It doubled its height. So as a result, you could say the world got half as tall. So y becomes y over 2. So as a result of that, we can say therefore y becomes y over 2. All right. So the equation is y over 2 is absolute x minus 3. And if you desired, you could solve for y. Finally, how about this one? What if I give you the equation? The equation is twice y is absolute x plus 1. So again, two proper motions. What are they? Okay, good. So this is saying left 1. Left 1. Or if you like, the axis is moving right 1. And then this is also saying something. It's going to be a scale. Okay, so I don't want to say down because that kind of means like right. So I'll say it like this: you're making the world twice as tall. So the object is going to be half as tall, right? So this height, this object, that point is at height 3. After we do this to it, what height is it going to be at? 1.5. It's going to be at 1.5. Okay, so alternatively, if you wanted to view it like that, if you're comfortable enough in saying that that means the object is twice as tall, then instead of multiplying by 2, what can I divide by? Multiplying by 2 is the same as dividing by half. So you could say that this is y divided by half you know, if you just wanted to view it that way. And then is absolute value of x minus -1. And then instead of saying you're going to move left 1, you could say I'm moving right -1. But then there's so many negations that most people's heads kind of say, no, I'm not going to say that. But, but okay, however you want to think about it. So left 1, so that means that this point, the pointy bit there, moved to there. And that green point also moved. So what is the horizontal coordinate of that point when we began? What was its horizontal coordinate? It was 3. So it's going to move left 1 unit. So what's going to be the new horizontal coordinate of the green point? It's going to be 2. So if that's 1 there, then that's 2. But because that represents a horizontal scale, no, a vertical scale of half. So that means that this point is at height 3. What's going to be its new height? 1.5. So it's going to be about this tall. So that's at the point 2 half. So it's an absolute value, but it's sort of shallower. Any question about this one? All right. Good. Now, here's a good question. We're talking about scaling stuff. Like if you scale the world horizontally by 2, that means that objects appear to be half as big horizontally. Okay. What if we scale the world by like -3 horizontally? What would that mean? That means that the objects have gotten smaller, right? So if you took your house and you said, you know, from the street, I'm going to make everything. I'm gonna multiply all the horizontal coordinates by 3. Then now your house would be like a lot wider, and you know, from your point of view, you'd be like narrower. But what if you multiplied it by -3? What would that mean? So to understand what that has to mean, please imagine the following. Imagine that you're standing, you know, you're getting ready for work or school or whatever, and you're looking in the mirror, and you can see yourself. And imagine in your mind's eye that you're holding up your right hand. And then what hand is the person in the mirror holding up? Their left hand. And vice versa. If you were holding up your left hand, the person in the mirror would be holding up their right hand. So isn't that curious that a mirror kind of, you know, seems to like reverse left and right? Why doesn't it reverse up and down? You know? How come when you're looking in a mirror, you're not upside down? That's a curious question. Now people are like, I can't even continue after that. We're gonna have to. Well, at any rate, can we agree that if you're looking in the mirror holding up your right hand, the person in the mirror is holding up the left? Okay. So you know, that's called a reflection. That's what a multiplication. That's what a negative scale looks like. Because what happens is that when you're looking at the mirror, the in and out direction has been reversed. Okay, so here we go. These are reflections. Is that you know, we can have a horizontal reflection. So if we take a graph there, so like that one, and so imagine that we just have one side. Okay, so we're just looking at, say, just that side, And the question is that if this red thing were, you know, a creature or whatever, and this vertical axis was a mirror, what would it see on the other side? Okay, and similarly, if we consider that bit right there, if that was, you know, just a little bit of a creature, and then that's a mirror, what would it see on the other side? So you know, originally that point was there, and this point was say here. So if that one point was looking in the mirror, and this vertical thing is a mirror, then it would see itself right there, right? It would see itself right there. And if this point was looking in a mirror, then where would it see itself? Over there, right? There-ish? So, you know, if I had the ability to draw, that'd be great. So that's supposed to be whatever. So alternatively, you can imagine something like this. Maybe you're, you know, making pancakes or something, and you dribbled out a pancake shaped like that. Okay, and then you know, you can grab this thing, pick it up, and turn it over and set it back down. That's what you'd see. Okay, so then because it's a horizontal reflection, we did not play with the y's. We played with the x's. So the y is the same. The f is the same because the structure's unchanged. But what does this become? X becomes negative x. All right. And if we can have a horizontal reflection, we can have a vertical one. So notably, in the horizontal reflection, there was a point that didn't move. Which point didn't move in the horizontal one? Right, that one right there. So that point didn't move. And we're going to do a vertical reflection. What point's not going to move? That one right there, right? Okay, so if we do a vertical reflection, then originally these points were here, here, and here. And then now, if these points were looking in the mirror, but the mirror was the horizontal axis now, then this one would see its reflection right there. Where would that one see its reflection? Same place, right? So on the mirror. And where would that one see its reflection? Up, right? So, you know, the picture would look something like this. So now it's again flipping the pancake, but doing it like this, twisting it this way. Okay, good. So here's a curious thing. Suppose that we have this y is x squared, and we do it for -2 less or equal x less or equal 2. Then, well, this is a you know, that's a part of a parabola, and parabola is something that you're required to know what it looks like. Yeah. So what would that look like if you did a horizontal reflection? So what would it look like? It would look exactly the same, right? So what I mean to say is, what if you grab this thing, grab this axis, pick it up, turn it over, and set it back down? What would the red look like? The same. So that's interesting. So this is a graph that is its own horizontal reflection. Now wait, algebraically, what does it mean to make a horizontal reflection? What do you do? Which variable do you play with? The x. And what is it that you do to the x? You negate. So what we're saying is that the new formula should be y is equal to, and then I've got to fill in the slot there, right? What goes in there? Negative x. And wait, can I algebraically simplify that? Does that simplify somehow?
Yeah, sure, yeah.
How does it simplify? The negative squares away, right? The negative squares away. So this is just equal to y is x squared. But wait a second, that's the same equation that we started with. So what I want you to see, and we're going to pick this up on Friday, what I want you to see is that notice that taking that graph and making a horizontal reflection does nothing. So that's a picture. But here's equations that are telling you the same thing. Translating x to negative x has no effect in the picture or algebraically. All right, have a nice Wednesday.